Everyone to one big table versus Kimball versus relational data modeling. This is a really meaty topic. There's a lot of things to cover. We're going to have a lot of ground to cover here. These are essentially the three main ways that you can model data. There are other options like Data Vault and other things that I am not covering in this presentation today because I don't think they're as important. So yeah, let's dig into this. So what will we cover today? How does data modeling generally happen? I think there's kind of some mystique and mystery around like how it actually happens, especially given the fact that like data modeling is a part art and a part science. So that is something that I think a lot of people don't really get. We're going to be covering that. We're going to be covering why do we need to model data in so many ways? Like why is there one big table and Kimball and Relational and Data Vault? And like why is there like a trillion million different ways? Aren't we just like modeling rows and columns? Like why the hell is there so many different options? So we're going to cover exactly why there are so many options. And then we're going to go over an in-depth example of comparing these three techniques and seeing like what the benefits and drawbacks are of Kimball, of one big table, of Relational. So you can kind of understand. And then we're going to also talk about like when does Kimball data model, when does it fail? And oh, then I have another extra line there. My bad, that was supposed to be deleted. Let's go. Okay, why are there so many data modeling techniques? The main reason for it is that each one has strengths and weaknesses. That's what it really comes down to. So when we get to the nuts and bolts of everything, you will notice that we have relational data modeling. That is like probably the most common. Relational data modeling you can think of as like another word I like to use for relational data modeling is production data modeling. So almost every production application is going to model data in this way. It's really, really good when you are filtering the data down to a small number of records, right? Think like filtering down to like one user or like a dozen events. It's really good for that, and it's really good at maintaining integrity because you have things like foreign keys and primary keys and deduplication and all this stuff where it enforces data integrity for most like relational database systems. So if you model your data in this way, like you get to leverage a lot of those quality guarantees. And that's what production databases are all about. And I mean, every company, you know, Netflix, Facebook, Airbnb, they almost all use some sort of relational database as their production data, like whether it be Facebook uses a sharded MySQL database, so does Airbnb. There's a lot of different SQL relational databases out there. So what are the cons of relational data modeling? Generally speaking, there's two big ones. The first big one is if you're doing an analytical question, you might need to join like 30 tables together. I remember when I was working at Airbnb trying to figure out like what are all of the pricing settings that are necessary to gather to understand like what things impact price. And that was a 25 table join. And it's like, imagine if that was every time an analyst needs to freaking understand what is impacting price, they have to do a 25 table join. So that's probably where you don't want to use relational. So generally speaking, relational data modeling does very poorly once you branch into analytics. When you're in analytics or you're in historical data, relational data modeling is going to suck, right? And the other big thing is relational data modeling generally is only for the latest state of the data. It doesn't have historical data. Okay. So Kimball or dimensional data modeling, this is probably the poster child. This is like probably the one that as data engineers you should know the most. It's the most important to know as a data engineer. If you've ever had a data engineering interview, then you know for sure that dimensional data modeling is asked. You're going to be you'll be given like some source data and then asked about like what are the dimension tables, what are the fact tables, what are the aggregate tables, and you have to come up with these little fancy diagrams. And I've been there. I've had to come up with those goddamn fancy diagrams so many times at Facebook, at Netflix, at Airbnb. I've had to do that many times in my interview processes. So that's great. It's really great for analytical processes, especially when you're converting to OLAP, right? If you're trying to like just get total aggregates and stuff like that, it's really great. It's also pretty good for large amounts of data and historical data. I found that like if you can do this stuff the right way, this is going to solve most of your problems. Like dimensional data modeling and dimensional and like dimensions and facts are going to cover like, I don't know, like 80 to 90% of your use cases that you want to do as a data engineer. And then there's going to be 10% or so that are going to be covered with like one big table. And then relational is kind of outside. That's like if you're doing application data modeling. So that's going to be the main things. So what are the drawbacks of dimensional data modeling? Like, I mean, transactions should be modeled relationally. Like transactions, like updates, don't really happen with dimensions and facts. Like you want to be like doing like a daily poll of this data. We're going to be looking at an architecture diagram here in just a second to see what is going on and what I mean by that. Let's just talk about the last one here. One big table data modeling. This is going to be on top of Kimball. Like, so you can think of it as like almost an extension of Kimball. It's like taking Kimball and denormalizing even more. That's the main thing that you can get out of like one big table. It's not like one big table and Kimball are really that different. They are a little bit different, and we're going to go into like where. So what one big table is really great for is you can answer questions minimizing joins and shuffle. So a lot of times, like you can think of one big table as like a table within a table. So, and the way that that works a lot of times is a table within a table means that you need to use complex data types. In this case, the complex data types are array and struct. Those are going to be the two. And a lot of times, like the table within a table here is actually an array of struct. So you actually put a table in a column. That's essentially what you do with one big table. It's kind of crazy. But what that does is it allows you to be able to do aggregations and sums without group by. You can actually just sum the array and you can get all that stuff out of it. We're going to be going over some examples here in just a little bit if it doesn't seem like something that makes that much sense. This is really, really great for long-term analysis. Like if you're working with a lot of data over a long period of time, it's really great because it minimizes shuffle. And if you're doing a long-term analysis, generally speaking, you have a lot of data that you're looking at. So it can minimize shuffle and make your queries more performant. It's bad because complex data types suck. Like, I don't know if y'all have ever tried to query array columns or struct columns, or teaching people how to query array and struct columns. People are like, fuck this. I don't want to learn this. This is not what I'm about. That's a big thing. I'd say that's the biggest con. Another very important con here is you essentially suck all of the fact data into the dimensional space. So a lot of times you end up copying a lot of the fact data over again. And so you end up denormalizing and copying data again. And that's the whole idea with one big table, is that like you are trading storage for compute, right? So you're saving a lot on compute by not having to do joins and not having to do shuffle. But where you're paying the penalty is in storage, because you're going to end up having like another copy of the data. And this can be very good though, because like, I don't know if y'all know, but storage, generally speaking, especially in the data lake, is really cheap. Compute is a little bit more expensive. So we'll go into a little bit more detail there later on. Okay, so in big tech and everywhere kind of in the world, if you are at a company that has any sort of advanced data architecture at all, this is the architecture that almost every single company uses. Like, it's kind of weird how consistent this architecture is across the board. So on the left, you have an application. Maybe that's Facebook, maybe that's Netflix, maybe that's Airbnb, maybe that's freaking Uber or Google or whatever. And then you have you or me, and then we interact with the production database through an application. Maybe we are booking an Airbnb, or we're adding a friend on Facebook, and we are updating and changing our production data. That is a very common thing. That is the production. That one arrow here, you see this one arrow right here. There's a lot going on there. A lot of but that's not our job as data engineers. Our job is in other places. This is like a software engineer, front end, back end, full stack engineer. This arrow has a lot of complexity to it that I'm not trying to minimize. I'm just trying to show what other things happen here. So when you do clicks and when you click buttons and stuff on an application or website, it also generates data, like generates fact data, like Zach clicked this button on February 29th at 8 p.m. And then that goes and gets dumped to Kafka. And Kafka, you can think of Kafka as a bunch of just like data waiting in a line. That's all Kafka is. And then we want to use Kafka to effectively capture all of the event data. And then, but the event data isn't enough because we also need the dimension data too. We need facts and dimensions in order to do dimensional data modeling. So generally speaking, you're playing around with the production data, and then on the back end, usually at 5 p.m. Pacific or midnight UTC, there are jobs that what they do is they look at the production data and they literally like do a select star from all the tables in production so that they know what the state of the data was at that moment in time. So like at midnight UTC, this is what was in production. And then they take that snapshot and then they dump it to a data lake. And then that is partitioned, right? That the data, the production snapshot for each table is in the data lake, but it's partitioned by snapshot date. A lot of times, like at Facebook and Netflix and Airbnb, they actually call it DS. So it stands for like date stamp. They don't call it snapshot date, but it's like DS. You can think of that as just like as of this moment in time. Along with the snapshotted dimensions that get dumped into the lake, you have the fact data that gets replicated from Kafka. A lot of times there's a bunch of different things that happen here. At Facebook, there's like an hourly Spark job that dumps it to the data lake, and then there's an hourly partitioned table there. Some places do daily, but whatever. The whole idea is we move the data from Kafka, put it into the lake, and now we are finally at a point where we can start doing our dimensional data modeling because we have all of the data in the data lake. We have our we have our facts data from Kafka, and we have our daily snapshotted data from production, from generally speaking, MySQL, but it can be other databases as well. So then after that, we go on to do our data modeling, right? We have master data, OLAP cubes, and metrics, generally speaking. Obviously, there's other things here like feature engineering, feature stores, machine learning stuff. If you wanted to like do other types of modeling as well, I'm trying to stick to more fundamental stuff in this presentation. So this diagram, I'll probably refer back to this at various points throughout this presentation so that if this was a lot to digest in the last 2 minutes, don't worry, we will be kind of coming back. Okay, so we're going to be covering an example here of user growth and engagement. So just imagine we are Facebook, right? And we have essentially 2 tables in production. We have the users table and the posts table. Those are going to be our 2 tables. And then we have a logging table, right? We have something that gets logged to Kafka. We have this post actions table. And post actions has the post ID, the user ID, the action type, and the action timestamp of like when. And the action type might be like, comment, share, whatever. It's just like an action that's done on a post. And then you have the user table, ID, name, country, all that stuff. You have the post table. This is great so far, right? So honestly, like from a relational perspective, that this is right? Because you see the post table has a foreign key with the user ID column. Great. So that means that there's a one-to-many relationship between users and posts. A post can only have one user, but a user can have many posts. That's what that relationship is talking about. That's why it's already modeled relationally. And generally speaking, as data engineers, we don't have to do very much relational modeling. I mean, unless you're at a very small company, then you're going to have to worry about this stuff as well. Like, for example, dataexpert.io, I do this modeling as well. I do the relational modeling and the dimensional modeling for my company. And so then you have we were talking about the post actions that gets dumped to Kafka. So the good news here is this data is already relationally pretty much correct. So you'll see, we have that one-to-many relationship, and luckily for us, the software engineer who modeled these tables, they did a good job. So we don't have to be frustrated with them. So keeping in mind that like if these tables are not modeled correctly in production, it's gonna mess up your analytics. So a lot of times, like if you have bad data that you snapshot, then that just is just bad data on top of bad data, and you have a problem, right? So that's where solving these problems in the relational layer is important. It's actually something that Joe Reese talked about in his data modeling stuff. He's talked about how really you have to normalize your data sets first in order to be able to then denormalize and do a lot of analytics on them. And I totally agree with that perspective. And so if your upstream production data is not modeled correctly relationally, you're going to have a pain in the ass time dealing with this. Whether or not you choose one big table or you choose Kimball, this is still going to be a massive pain in the ass for you. So make sure that like when you're looking at the production data that you look at the keys, make sure that maybe they even have like an ER diagram that models out like what the one-to-many and many-to-many relationships actually are, so that you can use that data downstream when you are doing your dimensional modeling or your one big table modeling. So that's a very important part of this data modeling process is you got to talk with the people who own the data, especially that upstream data, the data that's owned by the software engineers, whether that be the logging, right? The logging that's going to Kafka, or it can be the freaking dimensional snapshots or the production data. Like, I just want to give a quick aside here real quick. So when I worked at Facebook, we had this table called notifications delivery. And what it had in it was it logged every time a notification event happened. You can think about like a notification was generated, it was sent, it was delivered, it was clicked, right? All those different like events in the notification funnel. And one of the things that I didn't realize until I had been working there for a year was that they were logging every single experiment that a user was in at the notification grain though. So there was this big array that was all the experiments that a user was in, and they were logging it 50 billion times a day. And I learned that like after working in notifications for about a year, I discovered that, and I was like, we should delete that. And we don't need to do that. We can do a join between the user experiment table and the notification table, and then we don't have to have that big ass array replicated 50 billion times. And when we did that, when we actually deleted that column, we saved 3 petabytes of space in a month. 3 petabytes. And that was just deleting one column and then doing a join. So like a lot of times, like that's a big thing that I think data engineers don't do enough of, is they think that they have to solve everything in the data pipeline layer. They have to do it with Spark, with Airflow. That's where they need to solve their problems. But a lot of the time, you need to go upstream, and you need to have conversations with people and talk with people and have them fix the logging, have them fix the snapshots. And if you do that, that will be more fruitful. That one conversation saved Facebook 3 petabytes, right? And because I discovered that. And so that's just an example of where if you can do this stuff right, you can find all sorts of problems, because software engineers aren't that well versed in like cloud efficiency and a lot of these like dimensional data modeling things. They don't really think about that quite as much. They think about like, what is the way that we want to make this work? And especially what like, software engineers are going to make more errors in logging than they do in the dimensional space, in the dimensional snapshot space, mainly because the logging doesn't impact their job, right? Logging to them is almost like we're just sending these events off to be handled by somebody else. It's kind of like sending your kid to military school or like kicking them out of the house. It's like they're throwing it over the fence. It's someone else's problem now. And that someone else is the data engineer, and we get to deal with that. And so a lot of times you want to go back to them and be like, hey man, like, can you fix this problem? This is a mess. And so that generally happens more often with like logging and fact data than it does with dimensional data, because if they mess up the dimensional data, like their production app breaks. And so like then their app doesn't run, and then like you probably don't even get that data because the app is broken. So that's just a thing to think about when you're going through these data modeling exercises. Okay. What if we wanted to count the number of deleted posts that contain SQL sucks? That's what we want to do here with this relational data store. So if we go back, you can see we have this post text column. That's probably what we would want to do. But if it's the number of deleted posts, if we just look at production, we can't find it because it's deleted. It will be removed from production. So we can't solve this question with dimensional data modeling, right? Or with a relational data modeling, because of the fact that that data is actually deleted. So we actually won't be able to solve that problem. So another thing to think about is like we could maybe figure it out with the logged data, because the log data would have like a post action, which is a user deleted that post. So we maybe would be able to find it there. But the problem with that is we need to know the post contents. And the logged data will only have the post identifier. It's not going to have the post contents because that's bad, right? Because that's, again, duplicating logs, and like we don't want to do that. So how are we going to do this if the deleted post is going to disappear from production when it's deleted? So yeah, let's dig into it, see how we're going to do that. So this deleted post question is actually pretty simple. It's solved with snapshots, like I was talking before. Every day we take a snapshot of production at midnight UTC, and that gets dumped into the data lake. So then we have access to all the data for analytical purposes, whether it be like deleted or not in production. We know, like we still have a copy of it in our data lake. Generally speaking, this is one of those things that is kind of sensitive because it depends on your company's privacy policy on how this works. So at Facebook, how it works is if you have deleted data like that, you don't have a user ID, you have an anonymized user ID. So there's no way to link the user back to the post. There's no way to do that because it's an anonymized user ID. So the analytical data can still use it because it's anonymized and doesn't have any PII in it. So, but that depends on the company and the policy. But generally speaking, for the rest of this presentation, just recognize that the privacy policies that at this company are fairly lax. So remember, these database snapshots happen once a day. So we actually don't capture all the deleted posts, because if you create a post and then you delete it like in 5 minutes, the snapshotting process is not going to capture that. But you will be able to capture that in the logs, right? The logs will capture that you created and deleted a post, but we just we won't have any information about that post. And that's a very common thing where at a lot of companies, when you're measuring change that happens within a day, if something is created and deleted within a day, a lot of times like they just don't care about it. It's only like day over day change that companies care about. And that's why these daily snapshots are very, very useful. It doesn't capture the whole nuance of everything, but it does give you a pretty solid analytical picture into what's going on in your application. Okay, so let's think about it this way. So we say we are doing our snapshots, right? And now we have a new table here. This is going to be our new set of tables, right? Which are going to be our snapshotted tables and our table from Kafka. So now you see the user table here. We have a snapshot date. And then we have posts, which has a snapshot date. And these are going to be partitions in our data lake because we need to have folders for this data because we don't want to have to like query all the snapshots together because that doesn't make sense, because there's going to be a lot of duplicated data here. And we'll talk a little bit more about the benefits and risks of that. And then obviously the post actions table is going to have an action date partition as well. So those are going to be our 3 tables that are now in our data lake that are ready to do dimensional data modeling and one big table data modeling. And we're going to talk about the 2 different ways that we could possibly do this. Okay, so remember, we're trying to get the deleted posts. So to get the deleted posts, you could look at 2 snapshot dates and do a full add or join between today and yesterday. And then you can say where today.postID is null. Because if it's null today, that means it's not null yesterday, and that means it was deleted sometime between yesterday and today. This is a very common pattern. This is a part of what's called cumulative table design. I will have a link for that. If you go to my GitHub, you can find my cumulative table design. I have a lot longer write-up on that pattern specifically. It's a very powerful pattern that I highly recommend you check out. One of the things you'll notice about this snapshot stuff, right, is if we have a daily snapshot of the user table, how often does your name, email, and country change? I mean, I don't know. For me, my country has never changed. My email on Facebook has never changed. My name has. I went from Zachary to Zach. So I made one change, right, on like those columns. But we're taking a snapshot every day of my data, even though it's not changing. So that's actually kind of a waste, right? So one of the things that we need to do is notice that and notice like, hey, these things are not changing very much. They're changing, dare I say, very slowly. And so when if they're not changing very much and we're just taking all this snapshot, we're going to be having a lot of data in the cloud that we just don't really need, or that is just a lot of the same. So what we can do is we can convert these daily snapshotted dimensions into slowly changing dimensions. And this is a very important part of dimensional data modeling. And this is also a big part of one big table. We can talk about that in a little bit as well. So what we can do in that case, right, is imagine we have two tables here where we have the user's SCD table and the post's SCD table. So in this case, what we have is with the user table, the columns that can change is name, email, and country, right? You can change your name, you can change your email, you can move to a new country. And so those are the columns that can change. So that's why we can model those as an SCD. So what this will do is it will take those daily snapshots and kind of collapse them. So imagine if we, in a year, right? So there would be 365 records for me in a year because there's 365 daily snapshots. But say I only change my name once, and that's it. And my email and country don't change. I change my name once, email and country don't change. So if you model the SCD table, your 365 records should collapse into 2 records. Because you have the one record when you had Zach, and then you have another record when you had Zachary. And those are going to be the 2 records for when I change my name. And then, so that's what's really cool about modeling stuff as an SCD is you saw there, like going from 365 records to 2 records, that is a massive, massive performance gain in terms of storage. Right? And you can imagine the same thing for posts, right? In this case, there's only 2 columns, really. There's the is deleted column that would be modeled as an SCD, and then you have the post text column that would be modeled as an SCD, because you know how you can like edit a post? So then you could have kind of both in there as the 2 different columns that would be modeled as an SCD. And then everything else in these is the same. So this modeling here with the start date, end date, and is current, this is what's called SCD type 2. Slowly changing dimension type 2, which according to Airbnb is the only way to model slowly changing dimensions, because it's the only way that captures all of history, and it's the only way that you can correctly backfill SCDs. So just remember that, like, so SCD type 2 is going to be the gold standard, even though there is like SCD type 1, type 3, type 4, type 5, type 6, there's a lot of other types. Like type 2 is like the only one that you really need to know. And you can essentially derive all the other types from type 2, which I find pretty interesting. So anyways, those are going to be the 2 SCD tables that we could model if we were kind of going about this from a dimensional data modeling perspective, right? So let's dig a little deeper here. Okay, so now it's easy to count the number of deleted posts that contain SQL sucks, right? Because we can just say select count star from post SCD where post text like SQL sucks and is deleted is true and partition date equals this date. And then that will give us the current number of deleted posts that that have those words in them. So that is a very powerful way that you can model things. You see how that is a much better and simpler way to solve this problem versus doing it from the relational world where like we don't have access to that, right? Because we could do it from the daily snapshot data as well. The problem with the daily snapshot data is we would have to read in a lot of partitions. We'd have to read in a lot of partitions on a lot of extra data that like we don't necessarily need. And that's where this slowly changing dimension can be a very powerful way to solve this problem. So that's going to be the one thing that I want to talk about in terms of dimensional data modeling. Okay, so what if we wanted to ask something more complicated, right? What if we wanted to ask how many likes does a post containing SQL sucks get before it gets deleted? This is going to be a really solid question, right? Because in this case, we would need to do a join. Because you need to get the join between post SCD and post actions. That's how you're going to have to solve this problem, because that's going to be the only way that you can know to do that. But there is a big problem with this, right? And this is where Kimball kind of falls apart a little bit. Assuming that post actions is huge. We're going to assume that we're at the Facebook scale. The number of likes, comments, and shares on this posts is just very, very high. So in this case, so say you have a post that you want to know all of them together, all the posts that contain SQL sucks that were deleted, and we want to do a join with post actions to understand like how many likes each post got before they got deleted. So in that case, what you're going to need to do, right, is you would need to figure out the minimum created date and the maximum created date for posts that contain SQL sucks, which could be a massive window, right? Because someone in 2009 and someone in freaking 2018, they could be, I mean, you know how many people hate SQL? Like, it's a very consistent stream of hate, right? So, like, there's going to be posts every single day about it. So, in that case, you could do a join to figure this out with post actions, but you're going to have to look at essentially all of history in order to, all of history for post actions in order to get this right. Or, I mean, the other way to do this, right, would be, okay, we want to look at a specific time frame. Be like, and this is where you can kind of get away with this, right? Is like, okay, I only want to look at all the posts that contain SQL sucks in the last week, last month, last 6 months, or you pick like a specific time frame. But then you also need to pick like the other end, like for how long, because a post can get a like, right? I mean, like I get likes on some of my LinkedIn posts from 3 years ago. So like you're gonna have to have like a forward-looking cap as well. Like, so it's like, how many posts did something with SQL sucks from this 6-month window get for the next 2 years or the next 1 year, right? And you have to kind of put a freaking cap on it. That's going to be the way that you would solve this as efficiently as you could with Kimball data modeling, right? Because post actions is already modeled the way that you're supposed to do Kimball data modeling. Let's go back just to make sure that y'all remember that. So you see this post action table, it has the post ID on it, which is going to be that foreign key. It's going to have that link to that dimension. And that's what that's exactly the correct way to model Kimball data, Kimball fact data. So this is already a properly modeled Kimball fact data. So let's go back to this example here. I clicked a lot there. Okay, so now, like if you think about it this way, that's going to be a join, an inefficient join, and that's where Kimball is going to kind of fall apart. So what if we minimize the number of table scans here by incrementally building up arrays at the post grain? So in this case, imagine what we have here is a schema like this. We have one that has a post ID, actions, and a partition date. And then actions is every action that happens on a post. That is this new table. We're going to call this posts OBT. It's going to be a one big table post. So it's going to have the post ID and then every action that was taken on it. And so you can think about it this way. So every day what you do is you look at the new actions that come in and then you add them to this array. Just every day. You just do like an array concat between like the historical data and then the data that came in today. So you kind of incrementally build up this array every day. So then you can have access to all of the data that way. So if we do it this way, this can be a much more efficient way to know if you actually have all your data. And you don't have to worry about time frames quite as much either, because this is gonna be a cumulative table. This has every post, every action. But keeping in mind, again, that's where like this is a little bit inefficient because we are sucking all of post actions into posts OBT. You see we have that action type and action timestamp that's going to be sucked into this table. But then we can do really powerful things. So let's go into some queries here that I think y'all will find pretty interesting. So post OBT just has every single new event from post actions into an array of struct. And then we can reduce this array to get the current like count. And let me show you how that is done. So here's how you would do it and in this case, we're going to be using Trino/Presto, both for this presentation and for the lab today. So you'll notice here we have post OBT where the date, we have the partition date. And one of the things you'll see is we are actually getting the like count here, because what we do is we just take that array and we essentially, we start at 0. You see the 0 here. And then we do a case when on the action type inside of the struct. And we say, okay, if the action type is like, then add 1 to this. Otherwise, just have it still be the same. And that's what this reduce function ends up doing. So this is a way that you can get a like count without using group by, right? One of the things I want you to really notice here about this query is there is no group by, right? Because all of the events are already grouped. They're in that array. So it's already grouped. We've already done that work. So since there's no group by, this query is what's called infinitely scalable because it doesn't need any shuffle. There's no shuffle that is necessary here, right? This is the same as like a simple select. That's literally what's going on here. It's a simple select. So since it's a simple select, this is going to be a very, very fast query. So I leveraged this concept both at Facebook and at Airbnb for various things because this allows you to look at very large timescales and very long time periods without using very much compute at all because you don't have to shuffle. Because shuffle is where you're going to eat a lot of the pain and suffering of doing a lot of these long-term analyses. So let's go into the next page here to go into a little bit more detail here. So here is going to be kind of that final, this is going to give you that final example here of like how to get it, right? So in this case, we have our properly modeled posts SCD table, which we're still using, but then we have a little CTE here that gets our post count or our like count, and then we have we do a join with we join post SCD with that count, and then we just have the other conditions here, and then that is how we are going to go about doing this, right? That is going to give us everything that we're looking for. That is exactly the way that we would want to do this. So that is going to be this is like a very efficient way to solve this problem. But what I'm trying to say here is one big table is only very useful for a couple cases. But let's dig a little bit deeper here because some of y'all probably are thinking of like more efficient ways to do this without arrays. And you're totally right. You're totally right because guess what? There's another way to do this. There's another way to do this that isn't fucking crazy, right? So instead of sucking up all the event data into the post grain, you could do accumulated daily count. So imagine you created a table that's post likes cumulative, and what it is post ID and then like count, and then this count just every day gets added from, it looks at the new incoming data and it updates the like count. And then what we can do is we can just use this table, bada bing, bada boom, done, right? And then we don't have to do any crazy reduce shit. We don't have to do any arrays, no structs. And then we can solve that problem, that very narrow problem, right? This seems like a much simpler solution than everything I just showed you. And you're probably like, Zach, like, what are you smoking right now? Like, why are you showing me one big table? So this is the better way to go. If you are thinking about like one metric or like a couple metrics, right? Especially if they're metrics that don't have any other dimensional context that you care about. That's another thing to think about. So if we go let's go to the next slide, what I mean by dimensional context, right? So imagine we did this other design, this cumulative design, but then the data scientist comes back to us and is like, we want to now give me all the likes that happened between 4:20 p.m. and 4:25 p.m. each day to catch the stoned people liking the SQL Sucks posts. So now it's more complicated, right? Where now if we have to keep the timestamp around of when the likes happened, then this way of doing things, this post likes cumulative, is no longer going to work. It's no longer going to work, and it's not as flexible, right? This only gives you that total for the day or the total amount, right? You lose the factual, like that fact layer context if you aggregate up like this and make it simpler. And I'm not saying that this is wrong, and in a lot of cases, this is going to be 100% right and the correct way to do this, right? And that's the key thing to remember here is that this stuff is nuanced, right? That sometimes you do want to do this, and other times you want to maybe do one big table to keep the dimensional context. So let's think about this a little bit. So you see how like we have someone who wants just this 5-minute window each day. So you can imagine if we go back to this example with this reduce function, what we can do is we can add just a little bit here. So we can say case when x.action_type equals like and x.action_timestamp, like the hour and the minute of x.action_timestamp is between 4:20 and 4:25. So you would just add a very, very small addition to this query, and then you would have that context. And you wouldn't need to write another pipeline, right? You can just use this one again, and then you just have to throw it in this reduce function, and then you're good to go. And you don't have to build another pipeline. And so the one thing that this does, right, is this keeps the fact level data, right? You can understand more of each individual and each individual thing that's happening. You can be aware of those things, and you can go ahead and figure that stuff out as well. So that's essentially what I had for today in terms of my one big table versus dimensional modeling, right? So one big table preserves the fact, the other columns in the fact table that a lot of times you might need. A lot of times these columns are going to be like timestamps or maybe devices, or there could be all sorts of different other columns that you might want to also bring in here. So that's where this is going to be a much better way to do things versus the two other ways to do this, right? One is to just do it as normal fact data. The problem with that is that you're going to have to do you're going to have to scan hundreds of partitions of data in order to join it effectively, and that's not very fun. The other way to do this is going to be to do the cumulation with Kimball. And if you do the cumulation, the problem there is that you lose out on some of the event level context. And so if you have a data scientist who does want a very solid analytical architecture to work with, this is the way to go. One big table is the way to go. I want to give another example here. So when I worked at Facebook in 2017, Facebook saw the first drop in growth in the entire history of the company. So what happened was we wanted to dig through all of the data and understand all the slow burning, all the long-term trends. And what I did was I set up a one big table architecture so people can use these array functions and map them to dimensions, so then they can read 10 years of data very, very efficiently, and they don't have to shuffle